Hello my curious friend and welcome to Deepfield channel. Tonight we will drift away slowly, very slowly until the city lights shrink beyond reach, and then we will look upward to realize we have always been inside something immeasurable and quiet. The Milky Way, our galaxy, the home we have never seen from the outside. I promise to guide you through this cosmos as gently as possible, and I will do my best to keep the wonders soothing enough that they never steal your rest. Before we begin to float, I would love to know in the comments where in the world you are listening from tonight, and if you feel too drowsy to type much, just leave a simple hello. It may seem small, but that tiny gesture signals to YouTube that this is a welcoming space, helping us bring more tired minds here to unwind. If you enjoy these scientific journeys, please leave a like and subscribe. And to those already part of this community, thank you from the bottom of my heart. Now, wherever you are, settle into a truly comfortable position. Take a deep breath. If sleep arrives, welcome it. Let us begin. There is something you have done hundreds of times in your life that, on certain nights in certain places far from the artificial glow of cities, reveals what most people never truly pause to consider. You have looked up at the sky, perhaps on a beach, at a countryside cabin, on a dirt road inland, or during a camping night after the fires died and silence claimed everything. And there it was, a pale, softly glowing band, like a gentle mist stretching from horizon to horizon. You saw it without quite knowing what you were seeing. You were looking inward, into your own galaxy, from within it, using only your eyes. This is the first point that deserves our full attention tonight. The Milky Way is not something out there, distant, separated from you by some invisible border. You are inside it. You were born inside it. Earth is inside it. The sun is inside it. Everything humanity has ever touched, built, loved, or destroyed has happened within the boundaries of this colossal structure we call a galaxy. When you gaze at that milky streak overhead, you are not observing the Milky Way from the outside, like a painting on a wall. You are looking sideways along its flat plane, like someone lying in the middle of a dense forest trying to see the surrounding trees. You see the crowd of stars compressed along the galactic plane, and that crowd blends into the diffuse glow the ancients called the river of milk. And here begins one of the first gentlest surprises of our journey. For centuries, we looked at that band and assumed it was the universe itself. The ancient Greeks believed it was milk spilled by a goddess. Cultures across the world wove stories about that white path in the sky, tales of souls, deities, and bridges between realms. Even after science began to grasp the nature of those stars, a widespread conviction remained that our galaxy was all there was, that this collection of stars was everything. Generations of brilliant astronomers held this belief with absolute certainty. It seemed logical, it seemed enough. It was, after all, nearly impossible to imagine anything larger. The shift arrived in the early 20th century, and it remains one of the quietest yet most profound turning points in human understanding. An astronomer named Henrietta Swan Leavitt, working almost unnoticed at Harvard, uncovered a precise relationship between the brightness of certain variable stars and the time they take to pulse. This discovery allowed Edwin Hubble years later to aim a telescope at a fuzzy patch known as the Andromeda Nebula and realize it lay far beyond the Milky Way's boundaries. It was not a nebula inside our galaxy, it was another galaxy, an entire island of hundreds of billions of stars floating separately in space at a distance so vast it stumbles the tongue. In that moment, the universe expanded irreversibly within the human mind. And with that expansion came questions that still accompany us as we close our eyes at night. But before we look outward, we must truly know our home. And our home, the Milky Way, is already an object of such complexity and beauty that it could fill a lifetime of quiet wonder. The Milky Way is classified as a barred spiral galaxy. That label sounds simple, but it holds a geometry worth unfolding slowly. Picture a disk, not a small plate, but a disk of proportions that defy everyday comparison. Its thickness varies. Near the center, it swells into what astronomers call the bulge, a dense, ancient spherical core packed with old reddish stars that formed when the universe itself was still young. As you move outward toward the edges, the disk grows progressively thinner, like batter spread too far across a pan, becoming almost translucent at the rim. The total diameter of this disk is roughly 100,000 light-years. The light-year, a unit we will use often tonight, must be understood carefully because it carries a truth that can reshape how you perceive space and time together. A light-year is the distance light travels in one full year, and light, as you know, is the fastest thing in the universe. It moves at about 300,000 kilometers per second. In a single second, light reaches from Earth to the Moon with room to spare. In just over 8 minutes, it crosses from the Sun to Earth. Traveling at that staggering speed for an entire year, it covers a distance so vast that writing it in kilometers produces a number too large for the human brain to meaningfully grasp. And the Milky Way spans 100,000 of those distances, 100,000 years of travel at light speed from one edge to the other. If you departed today in a ship moving at light speed, which physics tells us is impossible, but let us imagine for a moment it would take you 100,000 years to cross our galaxy. 100,000 years. When anatomically modern humans first began exploring Africa, the Milky Way was already 100,000 light-years across. It has not changed much since. We have changed everything. Our Sun sits about 26,000 light-years from the galactic center. This means we are neither at the core nor at the farthest edges, but in a middle region, an area astronomers sometimes call the galactic habitable zone. It is far enough from the chaotic radiation-heavy center to remain relatively stable, yet close enough to have access to the heavier elements that ancient stars scattered into space when they died. There is a detail about our location that deserves a quiet pause. We reside within one of the galaxy's spiral arms. The Milky Way's spiral structure is not like a seashell's smooth, continuous curve from center to edge. It is more like a set of arms emerging from a central bar, a straightish bridge of stars and gas that cuts across the galactic core before curving outward, hence the name barred spiral. This central bar is difficult to see from our vantage point because it lies behind thick clouds of gas and dust that block visible light. We need infrared, radio, and X-ray telescopes to map what lies at the very heart of our home. The arm we inhabit is called the Orion Arm, or sometimes the Orion Spur, because it is smaller than the major arms. The two largest, densest arms are the Perseus Arm, farther out than we are, and the Scutum Centaurus Arm, closer to the center. We rest in a kind of corridor between them, a region of moderate density, away from the heaviest flows of stars and galactic gas. The disk's thickness in our neighborhood is about 1,000 light-years. It sounds small compared to the 100,000 light-year diameter, and it is. The disk is remarkably thin relative to its width, yet 1,000 light-years is still a distance our intuition cannot easily picture. It is a volume of space holding countless stars, planetary systems, gas clouds, dust pockets, and subtler structures science is still learning to chart. There is also a component of the Milky Way that never appears in those popular spiral galaxy images online because it is invisible to most of our instruments. It is the galactic halo. The halo is a diffuse spherical envelope that surrounds the entire disk like a bubble, stretching tens of thousands of light-years above and below the galactic plane. Within it drift extremely ancient stars, some of the oldest in the universe, gathered into tight spheres called globular clusters. each holding hundreds of thousands of stars scattered around the galaxy like floating ornaments. But the halo also holds something we cannot see, something that makes up most of the Milky Way's mass: dark matter. Dark matter is one of modern cosmology's greatest puzzles. We do not know what it is. We know it exists because galaxies, including ours, rotate in ways that make no sense if we only count the visible mass of stars, gas, and dust. Stars at the outer edges spin too quickly. If the galaxy's mass were only what we can see, gravity would be too weak to hold those stars in orbit. They should have flown off into intergalactic space long ago. The fact that they remain suggests there is far more mass than we see, spread across a vast halo around the disk. And this extra mass, this substance that emits no light, reflects no light, and absorbs no light in any way we have directly detected, is what we call dark matter. The most widely accepted estimate is that dark matter accounts for about 85% of the Milky Way's total mass. Everything we see, every shining star, every gas cloud, every speck of dust, makes up only 15%. We live inside a galaxy that is mostly made of something we cannot yet see or fully understand. There is something deeply human about this condition, dwelling in a home that conceals its own true nature. And speaking of star counts, another myth deserves gentle correction: the idea that we know exactly how many stars the Milky Way holds. The textbook figure often repeated is 200 to 400 billion. But this is a rough estimate with a wide margin of error. Counting stars in a galaxy is like trying to count grains of sand on a massive beach while only seeing a small patch. We use samples, mathematical models, total brightness measurements, and average stellar luminosity. The result is always an approximation, and astronomers are honest enough to keep that range broad. Even so, the most conservative number, 200 billion, is a figure that brings silence when you truly try to feel its weight. If you counted one star per second without stopping day and night, it would take over 6,000 years to reach 200 billion. All of human civilization, from the first Mesopotamian cities to today, would fit 20 times into that count. And when you finished, you would have counted only the stars in our galaxy, none of the others. Another fundamental aspect of the Milky Way that breaks a common visual myth is its actual appearance. When we see artistic renderings of the galaxy from above, it is painted in vivid blues and golds, with sharp, well-defined spiral arms that look almost printed. Reality is softer, more ambiguous. The spiral arms are not hard borders. They are regions of slightly higher density, where gas is a bit more compressed and therefore forms stars a bit more often. But stars exist throughout the entire disk, even between the arms. The galaxy does not have clean edges like a map. It gradually grows thinner and more sparse toward the outer regions, until at some point the disk simply fades into intergalactic space with no finish line. And the Milky Way is not still. The disk rotates. Stars orbit the galactic center, each at its own pace depending on its distance. The Sun, in its spot within the Orion Arm, takes roughly 225 to 250 million years to complete one full circuit around the center. This span of time has a poetic name, a galactic year or cosmic year. Over the Sun's 4.5 billion years of life, it has completed about 20 orbits around the galactic center. 20 galactic years. 20 grand rotations in an existence that already feels unimaginable in Earth years. While the Sun orbited, the entire history of life on Earth unfolded. The first bacteria appeared, oceans formed, continents drifted and collided, dinosaurs ruled for over 160 million years and vanished, and humans emerged in a tiny fraction of the most recent stretch of that journey. All of this happened while the Sun made its patient loops around the center of a galaxy that was already billions of years old before any of us existed. At the heart of all this, In the core of the Milky Way lies something that is not a star, not a gas cloud, not anything we can describe with everyday imagery. It is a region of gravity so intense that not even light can escape. A supermassive black hole named Sagittarius A. Its mass equals roughly 4 million times that of the Sun. Yet compared to the entire galaxy, it is tiny. Its radius is smaller than the distance between the Sun and Mercury's orbit, a small thing with immeasurable influence. For decades, its existence was a strong hypothesis supported by indirect evidence. Observations of stars orbiting near the galactic center showed speeds and paths that only made sense if a colossal concentrated mass sat at the point they circled. In 2022, the Event Horizon Telescope, a global network of observatories, captured the first direct image of Sagittarius A, a circular shadow, an orange ring of superheated matter surrounding a dark center, visual confirmation of what equations had predicted for decades. And it is this object at the center, this powerful silent darkness, that helps organize and maintain the galaxy's structure as we know it. Stars orbit around it. Spiral arms form partly under its influence. It does not actively devour the galaxy. It is not a hungry monster at the system's heart. Most of the time it rests quietly, feeding on small amounts of gas and dust that drift too close. But in earlier epochs it was far more active. Evidence suggests there were periods when enormous energy jets were expelled perpendicular to the disk, structures known as the Fermi bubbles, stretching tens of thousands of light years above and below the center, detected in gamma rays. All this energy, all this motion, all this structure stretching from the central black hole to the loneliest stars at the disk's edge exists thanks to forces working in silence, invisible to the eye, felt only through their effects. Gravity, pulling everything toward everything else. Radiation pressure from stars, pushing gas outward. Turbulence in interstellar clouds, sometimes collapsing inward, sometimes dispersing. And beneath it all, holding the entire structure together like an invisible frame, dark matter with its quiet gravity. But where does the energy come from that animates all of this? That spins the disk, ignites stars, launches jets from the core, keeps gas clouds in perpetual transformation. From cloud to star, from star to nova, from nova to nebula, from nebula to new star once more. Gravity has no color, no sound, no scent. If you could float in interstellar space thousands of light years from the sun with no nearby star bright enough to light your face, you would feel only the absolute cold of cosmic expansion and, at the same time, an imperceptible pull drawing your body towards something your eyes could not see. It would not feel dramatic. It would be like being called by someone whispering from the far side of an ocean. You would not hear the voice, but your body would lean, almost without meaning to, in the right direction. That is how the Milky Way works, not with violence, not with visible urgency, with a patience that has no human equivalent. The forces that move the entire galaxy are the same ones that drop an apple, keep the moon in orbit, and circulate blood through a heart. They are simple in nature and infinite in consequence. And understanding these forces is understanding why the galaxy exists as it does, why stars are born where they are, why the disk has its thickness, why the center shines so brightly while the edges remain quiet and sparse. The first force is the oldest we know, not the strongest, but the most persistent. Every particle with mass attracts every other particle with mass, without exception, without rest, without preference. A stone calls to another stone. A dust grain calls to another dust grain. A hydrogen cloud calls to another hydrogen cloud. And when those clouds are large enough and close enough, the call becomes irresistible. The cloud begins to fall inward slowly at first, then with ever-growing speed. It is the beginning of almost everything in the galaxy. Isaac Newton recognized this in a moment that history has romanticized more than reality likely warrants. Perhaps it was not a falling apple. Perhaps it was simply a long night of calculations, an extraordinarily disciplined mind spotting a pattern hidden within observations others had made but could not connect. Newton asked the right question. Is the force that drops the apple the same force that holds the moon in orbit? The answer was yes. And with that answer, he forever changed how humanity understands the cosmos. The law he wrote states that the force between two bodies is proportional to the product of their masses and inversely proportional to the square of the distance between them. In everyday terms, this means the larger the body, the stronger the pull, and the farther away you are, the weaker that pull becomes, not linearly, but quadratically. Double the distance, the force drops to a quarter. Triple it, it drops to a ninth. It is a law of rapid fading, but never complete disappearance. The gravity of every star in the Milky Way touches, in some infinitesimal way, every other star in the Milky Way. The entire galaxy is in constant gravitational conversation with itself, and that conversation never stops. What Newton could not explain was the deep nature of that force. How can two bodies that never touch influence each other? He admitted he did not know. He called it action at a distance and confessed it seemed absurd to him, yet it worked. The mathematics was correct even without the explanation. And for nearly 250 years humanity used Newton's equations to navigate planets, predict eclipses, and calculate comet orbits without ever fully understanding why they worked. The explanation arrived with Albert Einstein in a century that began with physics convinced it understood the universe and ended with it completely transformed. Einstein imagined something Newton had not considered. Space and time are not merely the stage where events occur. They are active participants. Matter with mass bends the space around it, creating curvature, and what we call gravity is simply the motion of bodies following those curves. Like a marble rolling across a stretched sheet where you have placed a weight in the center. The marble is not pulled by magic, it simply follows the shape of the fabric. This image, which Einstein developed over years of intellectual effort, he described as the most demanding of his life, profoundly changed our understanding of the Milky Way. Because on a galactic scale, space is not flat, it is full of curves. Every star creates its own small dip in the geometry of space. The galactic center, with its immense concentration of mass, including the supermassive black hole, creates a profoundly deep well, and everything around it responds to that curvature, orbiting, approaching, retreating in patterns that are the direct expression of the geometry matter imprints on space. But gravity alone does not explain everything. If it were only gravity, gas clouds would collapse instantly, and all the galaxy's matter would be crushed into the center in far less time than the galaxy has existed. Something must push back, and there is. The second major force at play in the Milky Way is pressure in all its forms. The pressure of hot gas resisting compression, the pressure of stellar radiation pushing interstellar gas outward, the pressure of supernova shockwaves rippling through the interstellar medium like waves across a disturbed pond. And, on the most intimate scales, the internal pressure of stars themselves, balancing gravitational collapse against thermal expansion. Imagine holding a hot air balloon between your hands. The air inside tries to expand it. Your hands, pressing from outside, try to shrink it. The balloon exists in that balance between internal and external pressure. A star is that balloon, but with a crucial difference. The internal pressure does not come merely from leftover heat. It comes from a process that stands as one of the 20th century's most astonishing discoveries, a process happening in the core of every star you see in the night sky, a process that released the energy warming Earth's oceans for billions of years, that created every heavy element in your body. Nuclear fusion. Two hydrogen nuclei pushed together with enough speed and pressure merge to form a helium nucleus, and in that merger, a small amount of mass vanishes. It is not lost, it transforms. Following the equation Einstein derived as a direct consequence of his special theory of relativity, that lost mass converts into pure energy, and the amount released equals the mass multiplied by the square of the speed of light. The speed of light is so vast and its square so immense that a minuscule amount of mass becomes a colossal amount of energy. Our Sun converts about 4 million tons of mass into energy every second. Not through combustion, not through chemical reaction, but through nuclear transmutation. 4 million tons per second, and yet the Sun has enough mass to keep doing this for another 5 billion years. The scale defies human visualization. But within the Milky Way, the Sun is just one of hundreds of billions of stars doing the same thing, each at its own pace, each turning hydrogen inherited from the primordial nebula into helium, into heat, into light, into pressure. The discovery of stellar fusion carries a human story involving war, political persecution, and one of the last century's most elegant intellectual syntheses. Hans Bethe, a German physicist who fled Nazi Germany and found refuge in the United States, was the one who finally detailed how stars convert hydrogen into helium. In 1939, 2 years before America entered World War II, he published a paper describing the CNO cycle and the proton-proton chain, the two main fusion mechanisms powering stars. Later, he worked on the Manhattan Project, a historical irony he carried with ambivalence for the rest of his life. But his contribution to astrophysics remains. Bethe gave us the key to understanding why stars shine. Before Bethe, there were proposals and guesses. The geologist Lord Kelvin calculated in the 19th century that the Sun could be only 20 million years old if its energy came from gravitational contraction. Biologists and geologists of the era knew Earth was far older, but there was no way to contradict Kelvin without an alternative energy source. Henry Becquerel's discovery of radioactivity in 1896 and the later realization that atomic nuclei held immense energy opened the door. Bethe closed the argument. Stars do not burn, they fuse. And that fusion is an energy source so efficient it can sustain a star like the Sun for 10 billion years. The balance between gravity and radiation pressure has a technical name astrophysicists use often: hydrostatic equilibrium, but beneath the term lies a dance that is in its own way moving to contemplate. A star exists because two opposing forces are in perfect balance, and that balance is dynamic, not static. If the star cools slightly, pressure drops, gravity compresses it a bit more, the core heats up, fusion accelerates, pressure rises and pushes back. If the star overheats, it expands. The core eases, fusion slows, the star contracts again. It is a self-regulating feedback system that finds equilibrium without any external mechanism, purely through physical laws acting on matter. This self-regulating capacity is what makes stars so stable, so long-lived, so unlike anything we build in laboratories. A fusion bomb releases its energy all at once, uncontrolled. A star releases its energy slowly over billions of years because the pressure created by expansion immediately counteracts any increase in fusion rate. It is like a cosmic thermostat, but made of pure physics with no moving parts, no electronics, just gravity and pressure conversing in a language older than any civilization. But not everything that sustains the Milky Way is visible or fully understood. There is a third component, discovered much later than gravity and pressure, and still shrouded in mystery today. Vera Rubin was an American astronomer who in the 1960s and 70s studied the rotation of spiral galaxies with a patience and precision that many of her contemporaries who doubted the effort would be worthwhile, could not imagine would lead where it did. What Rubin measured was the speed at which different parts of a spiral galaxy orbit the center. The expectation based on visible light distribution was that stars at the edges would orbit more slowly, just as outer planets in our solar system move slower than inner ones, because they are farther from the center of mass and gravitational pull is weaker. But what Rubin found was different. Stars at the edges orbited at nearly the same speed as stars closer to the center. The rotation curve was flat when it should have declined. There is only one explanation for this within known physics. There must be far more mass in the system than visible light reveals. Mass that emits no light, absorbs no light, interacts in no way we can directly detect, but whose gravitational presence bends rotation curves and keeps galactic edges moving faster than any calculation based on visible matter could predict. This substance was named dark matter, and we now know it makes up most of the Milky Way's mass. Dark matter does not form stars, it does not form planets, it does not form visible clouds. It appears to distribute itself in a vast sphere around the visible disk, in a halo stretching tens or hundreds of thousands of light years beyond the farthest star any telescope has detected. It is like the invisible frame Rubin did not know she was searching for, but found anyway. The galaxy you see in a long exposure photograph, with its spiral arms and luminous center, is only the part that emits light. The real structure, the one gravity traces in space, is far larger and completely invisible. We do not know what dark matter is. Decades of experiments, underground detectors waiting for signals from unknown particles, particle colliders trying to create them in labs, telescopes searching for indirect gamma-ray signatures of dark matter annihilation, have not yet produced a definitive answer. It may be made of particles physics knows but has not directly detected. It may be something entirely new outside the standard model summarizing our current knowledge of fundamental particles. It is even possible the solution lies in modifying gravity itself on large scales, though that hypothesis faces its own challenges. What is certain is the effect. Without dark matter, the Milky Way would not have its current shape. It would not rotate as it does. It would not have held together over billions of years of history. The disk's edges would have unraveled, the outermost stars would have escaped into intergalactic space, and the spiral structure we see would be impossible. Dark matter is the galaxy's skeleton, the gravitational framework upon which all visible matter organizes itself. Discovering its nature remains one of today's greatest open goals in fundamental physics. The three forces, the gravity of visible matter, the pressure of radiation and gas, and the silent gravity of dark matter, interact in ways that are never completely predictable in detail, but follow a general pattern we recognize. A gas cloud begins to contract under its own gravity. It fragments. Each fragment collapses faster. The center of each fragment heats up. Pressure builds. At some point, nuclear fusion ignites and radiation pressure enters as a new player, pushing surrounding gas outward, dispersing material that had not yet collapsed but might have formed more stars. A nearby supernova sends a shockwave that both compresses neighboring clouds, potentially triggering new collapses, and heats and disperses them, potentially preventing others. The interstellar magnetic field, weaving through the galaxy like a web of invisible force lines, resists the collapse of some clouds and aids others. It is a system of complexity that defies any attempt at complete simulation. The world's largest supercomputers spend months calculating the evolution of a small region of the interstellar medium, considering only a few of the mechanisms at play. Even so, simulations reveal patterns that observation later confirms, suggesting physical laws are being applied correctly, even when individual details remain impossible to predict. The fundamental imbalance that makes all this work is simple to state, though rich in consequences. Gravity tends to gather, pressure tends to scatter. Neither ever wins completely. In a young galaxy, with abundant cold gas and few stars to heat it, gravity wins often and stars are born in great numbers. In a mature galaxy like the Milky Way, with much gas already turned into stars and significant residual heat in the interstellar medium, the balance is more delicate and the star formation rate is lower. But the game never stops. There is always some cloud contracting somewhere in the disk. Always some new star igniting fusion for the first time. Always some supernova returning to the interstellar medium what an earlier generation of stars had consumed. In a specific nebula today, right now, a dense gas filament is beginning to fragment. Each fragment is accelerating its collapse. In a few 100,000 years, some of those fragments will have ignited fusion in their cores. They will be stars. Each will be unique, the result of a series of gravitational and turbulent accidents that will never repeat exactly. Each will carry the elements the original cloud contained, forged by earlier generations of stars, and will scatter them back into the cosmos when its life ends. And then the question this mechanism poses when you contemplate not a cloud fragment, not a nebula, not an isolated spiral arm, but the entire galaxy with its hundreds of billions of stars and countless clouds and intertwined magnetic fields and silent dark matter cloak, is this: what happens when this same process, this collapse and ignition and death and redistribution, repeats hundreds of billions of times over 10 billion years across every corner of a disk 100,000 light-years wide? The answer science has built for that question did not arrive all at once. It accumulated over decades in isolated observatories and on paper covered in handwritten equations, on nights when astronomers pointed their instruments at a pale band in the sky and tried to understand why it had that particular shape, why it glowed that way, why some regions were dense and others nearly empty. The answer arrived in fragments just as the galaxy itself reached its current form, and each fragment revealed that the process described earlier on a local scale was merely one link in a much longer chain. The first link to understand is that the Milky Way is not a collection of independent stars, it is a system. And the difference between a collection and a system is precisely the existence of relationships that transform the behavior of each part. When we say the galaxy holds hundreds of billions of stars, that phrase sounds like a description of abundance, as if we were talking about sand grains on a beach. But sand grains on a beach do not noticeably influence each other. Stars in a galaxy do, and not only through direct gravity between pairs, but through intermediate structures, scales that connect the individual to the global in ways that took generations of physicists to begin to grasp. The first of these intermediate structures is the spiral arm itself. For a long time it was treated as a morphological curiosity, an aesthetic feature, something that distinguished it from elliptical or irregular galaxies, but did not necessarily have a deep dynamic explanation. We knew arms existed because images of similar galaxies showed the pattern clearly. We knew the Milky Way must have them because star counts and gas regions along the galactic plane showed specific concentrations. But why arms existed, how they persisted, remained completely open until the second half of the 20th century. The most puzzling problem was what astronomers called the winding dilemma. Imagine spiral arms were material structures, meaning the same stars forming an arm today would be the same ones forming it tomorrow and a billion years from now. If that were true, and if different parts of the galaxy orbit the center at different speeds, which they do, then over a few billion years the arms would have wound around the galactic center so many times they would no longer be recognizable arms. They would be lines so tightly packed the galaxy would appear smooth, structureless. But spiral galaxies exist, and they are abundant. That is the paradox. The solution came from two physicists working at MIT in the 1960s, Chia Qiaolin and Frank Xu. They proposed that spiral arms are not material structures, they are density waves. The distinction is subtle but fundamental. Think of a highway on a Saturday afternoon, with traffic flowing reasonably well but with a slowdown that propagates opposite to the traffic flow, a spot where cars briefly bunch up before accelerating again. The cars making up that bunch are not always the same. Each car enters the slow zone, decelerates, and leaves it. But the high-density region, the slowdown itself, can travel along the road as if it were its own entity, even though the material composing it is constantly changing. Spiral arms work analogously. There is a compression wave traveling along the galactic disk with its own angular speed different from the speed at which individual stars orbit. When stars and gas clouds enter a region of higher gravitational density, they slow slightly, compress, and then continue on their way. The arm is the region of compression, not the material passing through it. This solves the winding dilemma because the density wave can maintain its shape while the matter composing it flows continuously through it. But density wave theory did more than explain why arms do not wind up. It revealed that arms are active organizing mechanisms. When an interstellar gas cloud enters a spiral arm, it experiences additional pressure. That pressure favors gravitational collapse. Clouds that were already marginally unstable, already near the threshold of forming stars on their own, are pushed past that threshold by passing through the higher density region. This is why star-forming regions, the nebulae described earlier in detail, concentrate along spiral arms. Arms are not just where young stars are, they are where young stars are born because the density wave precipitates the formation process. This creates an extraordinary global pattern. Looking at the galaxy from above, if that were possible, we would see arms outlined not only by existing stars but by glowing red gas clouds, illuminated by the radiation of newborn stars living inside them. Star formation is not randomly distributed across the disk. It follows the arms, and the arms follow the density wave, and the density wave is an emergent property of the disk as a whole, from the collective gravitational interaction of all its parts. No individual star, no individual cloud decided to organize this way. The structure emerged from the system. This idea of emergence, of patterns, that no individual component planned or knows, but that arise from local interactions among many components, is perhaps the most important concept for understanding the Milky Way on a large scale. And it is not limited to spiral arms. It appears at multiple scales and in multiple phenomena, creating a galaxy far more organized than the simple sum of its parts would suggest. Consider the age distribution of stars in the disk. If star formation were a purely local process, without memory or coordination, we would expect to find stars of all ages randomly mixed throughout the disk. But that is not what we find. There is a gradient. Older stars tend to be farther from the disk's mid-plane, more vertically dispersed. Younger stars tend to be concentrated in the plane near the gas clouds from which they emerged. This pattern has a dynamic explanation connecting the local to the global. When a star is born, it forms in a gas cloud close to the galactic plane, because that is where gas concentrates due to the disk's gravity. The star begins its life in this relatively dense, flat region. But over its lifetime, it experiences gravitational perturbations. Passing gas clouds, encounters with other stars, the influence of spiral arms it crosses repeatedly. Each of these perturbations, on average, adds a little energy to the star's vertical motion, pushing it slightly above or below the plane. Over billions of years, This process of gravitational heating, which astronomers call secular heating, causes the star to oscillate increasingly widely above and below the plane. The result is that a star's age is written in the amplitude of its vertical oscillation. A star that barely strays from the plane is young. One that oscillates hundreds of light years above and below is old. The disk's thickness is, in this sense, a library of galactic history, and that thickness has two layers astronomers distinguish: a thin disk, where younger stars and gas live, and a thick disk inhabited by older populations, heated by billions of years of gravitational encounters. These two overlapping disks were not built intentionally. They emerged from the statistics of billions of individual interactions over billions of years. The geometry of galactic rotation itself also imposes an order that influences everything else. The Milky Way does not spin like a solid wheel, where everything completes a rotation in the same time. Different radii orbit at different angular speeds in a pattern called differential rotation. Regions closer to the center tend to complete their orbits faster than more distant regions, though the pattern is not as simple as a solar system because the galaxy's mass is distributed throughout the disk rather than concentrated at a center. This differential rotation has profound structural consequences. Any feature initially aligned radially, like a denser gas patch stretching from the center outward, will gradually be distorted into an arc by the speed difference between its inner and outer ends. Over time, that arc wraps around itself and the structure loses its original shape. It is part of the mechanism that helps raise structures too simple to survive galactic dynamics. But differential rotation also does something constructive. It amplifies irregularities. A region that accidentally has slightly higher density than its neighbors attracts more matter gravitationally. But differential rotation stretches that accumulation along the orbital direction, creating an elongated structure. And structures elongated along the orbital direction are exactly the geometry of spiral arms. Some models suggest that even without a propagating density wave, differential rotation alone, acting on random disk irregularities, would tend to produce transient spiral features. The galaxy has an intrinsic tendency towards spirals, inscribed in the very geometry of its rotation. On an even larger scale, there is the structure connecting the disk to the halo. The Milky Way's disk does not exist in a vacuum. It is immersed in a roughly spherical halo of much more diffuse, much older, and much less organized material. Halo stars orbit the galactic center in highly elliptical, inclined paths without the ordered rotation pattern characterizing the disk. Many are the oldest stars in the galaxy, formed in the first few billion years after the Big Bang, when the galaxy was young and its organizing processes were still establishing themselves. Astronomer Walter Baade, working at Mount Wilson Observatory in the 1940s, was the first to clearly articulate the distinction between what he called Population 1, the younger, heavy element-rich stars inhabiting the disk, and Population 2, the older, chemically simpler stars of the halo and central bulge. This distinction was not merely descriptive, it was a window into galactic history. Population 2, stars formed before earlier generations, had time to enrich the interstellar medium with carbon, oxygen, iron, and other elements stars produce and release. Population I stars, by contrast, were born from already processed, already enriched material, already carrying the chemical inheritance of predecessors that lived and died before them. The distribution of these two populations across the galaxy is, therefore, a map of time. The halo is ancient. The disk, on average, is younger, though it contains stars of a huge variety of ages. The central bulge, the compact bright region at the galaxy's heart, contains both very old stars and more recent populations, the product of a more complex and intense star formation history than occurs in the quiet disk where the Sun resides. And the Sun, in this large-scale context, occupies a position with its own implications. It sits about 26,000 light-years from the galactic center, in a region between two major spiral arms, in a place astronomers sometimes call the Orion Arm, which is more of a spur, a minor branch, than a full primary arm. It is a peripheral location, far from the extreme densities of the central bulge and far from the most active star-forming regions in the main arms. A location in certain senses tranquil. That tranquility is not trivial. In the galactic bulge, stars are much closer together. Disruptive gravitational encounters are far more frequent. Radiation from densely packed stars is more intense. At the very center lies the supermassive black hole, which, when active, can emit energy jets radiating across the galaxy. Inhabiting the outer disk between spiral arms far from the center, places a solar system in a relatively calm, relatively predictable, relatively stable neighborhood over the timescales complex life needs to develop. Astronomer Guillermo Gonzalez, in the late 20th century, developed the concept of the galactic habitable zone, by analogy with the stellar habitable zone, describing the optimal distance from a star for a planet to hold liquid water. The galactic habitable zone would be a band of radii around the galactic center where conditions are stable enough and rich enough in heavy elements to allow complex worlds. Too close to the center, galactic violence is excessive. Too far out, gas was never sufficiently enriched in metals to build rocky planets. The Sun inhabits an intermediate region satisfying both conditions, but returning to emergent structures themselves, there is an aspect of the galactic disk that took decades to be properly mapped and reveals a particularly interesting global organization. The disk is not flat, it has a slight warp, like the brim of a hat gently bent in one direction. This phenomenon, called disk warping, is more pronounced in the galaxy's outer regions, far from the center, and its specific orientation suggests it was produced by the gravitational influence of satellite galaxies orbiting the Milky Way, particularly the Magellanic Clouds. The disk as a whole responds gravitationally to external structures surrounding it, and this warp is the scar of that response. The Magellanic Clouds themselves are an example of how the Milky Way's large-scale order extends beyond its formal boundaries. These two smaller galaxies, visible from the southern hemisphere as luminous patches in the sky, orbit the Milky Way on a path that has brought them progressively closer over billions of years. The gravitational tide the Milky Way exerts on them has stripped material from their structures, creating what is called the Magellanic Stream, a gas band stretching across a huge fraction of the sky and slowly feeding the Milky Way's outer disk with fresh material. These interactions between the Milky Way and its satellites are not external disturbances to an otherwise closed system. They are constitutive parts of the galaxy's history and structure. The Milky Way reached its current state not only through internal processes but through a series of interactions, minor mergers, and external material accumulations, leaving structural records readable to those who know where to look, in the peculiar orbits of certain halo stars, in the chemical composition of certain stellar streams crossing the disk, in traces of dwarf galaxies the Milky Way absorbed over billions of years, whose remains continue orbiting like dissolved ghosts in the halo. Jan Oort, the Dutch astronomer who made fundamental contributions to understanding galactic structure in the 20th century, including the first reasonable estimate of the Sun's position relative to the galactic center, described mapping the galaxy from within as trying to draw a forest map while standing inside it, unable to step out. The analogy captures the challenge but perhaps underestimates the richness of methods astronomers developed to compensate. Hydrogen radiation in radio waves penetrating interstellar dust, opaque to visible light, allowed mapping gas distribution across the disk. Spectroscopy revealed rotation speeds of different regions. Recent space missions, especially the European Space Agency's Gaia mission, measured positions and motions of over 1 billion stars with unprecedented precision, revealing halo structures and streams invisible any other way. And what all this cartography reveals is a galaxy simultaneously more ordered and more complex than any simple model could capture. Ordered because the large patterns, spiral arms, age gradients, population separation, disk warping are real, reproducible, and have coherent dynamic explanations. Complex because within each pattern exist substructures, exceptions, local histories. The global pattern does not completely determine. The order is statistical, not absolute. It is the order of a system with many parts interacting over a long time, where regularities emerge from the average of countless individual events, but where no individual event is completely determined by the global pattern. There is something deeply satisfying in this image, and also something inviting an additional question. The order described so far, the order of spiral arms and stellar populations and the disk with its thin and thick layers, is an order that would emerge even in a galaxy made only of visible matter, gas and stars and dust emitting and absorbing light. But the Milky Way is not made only of that, and the difference between what that simpler galaxy would be and what the Milky Way actually is, that difference is not small. It is the difference between a galaxy that would exist for a while and dissipate and a galaxy that has the shape, mass, and permanence we observe. The ingredient making that difference remains silent, emits no light at any wavelength our instruments can detect, yet governs the trajectory of every orbiting star, shapes the outline of every spiral arm, and determines the future of the entire structure. Its presence is known only by the effects it causes on what is visible, like space curvature around a mass no eye can see. This silent ingredient governing every star's trajectory did not enter human knowledge all at once. There was no morning when someone woke certain that most of the universe's mass would be invisible. Understanding came through accumulation, through stubborn repetition of an anomaly that refused to disappear no matter how many alternative explanations were tried. And the anomaly was simple to state, though profound to accept. Stars at the Milky Way's outer edges orbit too fast. When a planet orbits the Sun, its speed decreases with distance. Mercury races frantically, nearly torn apart by heat and central pull. Neptune, in the solar system's cold margins, glides with a slowness taking over 160 years to complete a single lap. This relationship between distance and speed is so precise, so mathematically inevitable, that for centuries no one imagined it could differ in any gravitational system. The law governing Mercury and Neptune should also govern stars in spiral arms and stars at galactic edges, but it does not. And this discrepancy, which could be dismissed as measurement error in the early 20th century, became impossible to ignore when instruments improved enough to measure distant stars' speeds with growing precision. An astronomer named Vera Rubin, working in the late 20th century with a spectrograph capable of splitting galaxy light into individual frequencies, found something contradicting all expectations. Stars at the outer edges of spiral galaxies did not slow down. They spun at nearly the same speed as stars near the center, and this behavior was only possible if additional mass, far more than visible, was distributed spherically around the entire galaxy at distances where no bright star was observed. Vera Rubin was not alone in this discovery. Other voices, other data, other approaches reached the same conclusion independently. Fritz Zwicky, decades earlier, had calculated a galaxy cluster's total mass using two distinct methods, by emitted light and by galaxy motion within the cluster. The two results should have matched. They did not. The mass calculated from motion was hundreds of times greater than the mass calculated from light. Zwicky called what was missing dark matter Dunkelmaterie in German, and the name stuck even though the substance itself remained completely unknown. What we know today is that the Milky Way exists within a structure far larger than its spiral arms or central bulge suggest. Around everything visible, around the disk with its thin and thick layers, around the bulge with its aged stellar population, lies an immense spherical halo stretching hundreds of thousands of light years in every direction. This halo emits no light, reflects no light, absorbs no light in ways our instruments can record, but it has mass. It has mass in a way felt in everything within it, in every orbit, in every spiral arm, in the very shape and cohesion of the galaxy. This dark halo's mass is estimated at roughly 6 times the total mass of all the Milky Way's visible matter. 6 times. That means if you could weigh every star, every dust grain, every gas filament and molecular cloud in the galaxy and place that weight on a scale, the dark matter halo would weigh 6 times more on the other side. The galaxy we see when we look at the night sky, that luminous band stretching horizon to horizon, is only a fraction of the real Milky Way. It is the part that shines. Most of it does not. Here, the most accurate analogy is not a shadow accompanying something lit. A shadow depends on the light of the object casting it. Dark matter does not depend on luminous matter. It would exist, have mass, exert gravity, even if there were not a single star in the universe. The truer analogy is perhaps a skeleton, not in a macabre sense, but in a structural one. The skeleton is not seen from outside. What is seen is skin, muscle, face. But the skeleton determines form, supports structure, distributes forces, making movement possible. Without it, what is visible would collapse into something shapeless. Dark matter is the cosmos's skeleton, and the mechanism by which it amplifies and sustains the Milky Way is entirely gravitational. No new force, no exotic interaction, no unknown field needs invoking to explain its effects. Ordinary gravity, the same keeping the moon around Earth, Earth around Sun, and Sun around the galactic center, is the only known force dark matter exerts. But because it has so much mass and because that mass is distributed to envelop the entire galaxy in a huge sphere, its gravitational effects are deep and pervasive. Think of the difference between a shallow basin and a deep one. If you place a marble in a shallow basin and give it a small push, it climbs the edge, escapes, and is lost. If you place the same marble in a deep basin and give the same push, it oscillates, rises, falls, and eventually remains inside, contained by the depth of the gravitational well. Dark matter deepens the Milky Way's gravitational well so that stars that would otherwise escape, that would be flung into intergalactic space by speeds acquired over billions of years of interactions, remain. The galaxy retains its stars not because they lack escape velocity, but because the well is deep enough to hold them. This deepening of the gravitational well also explains why spiral arms exist in the form they do. Without dark matter, spiral arms would dissolve much faster. Outer stars in particular would disperse before observed patterns had time to form. Dark matter does not create arms directly, does not shape them with some invisible hand, but creates conditions of permanence, allowing density wave patterns to persist long enough to be observable. It is a subtle but fundamental difference, the difference between a fleeting pattern and a lasting one. Visible manifestations of dark matter are, by definition, indirect. You never see dark matter itself. You see what it does to surrounding light and what it does to the motion of things within its influence. One such manifestation is gravitational lensing. When a massive cluster of matter visible and invisible, sits between a distant light source and an observer. The mass curves space around it, and light traveling through that curved space follows paths it would not in flat space. The visible result is light arcs, multiplied images, subtle distortions in background galaxies' appearances, revealing mass presence and distribution even where nothing is seen. Some of these gravitational lenses are spectacular. There are configurations where a background galaxy appears multiplied into 4 images arranged around a central point, a pattern astronomers call an Einstein cross, honoring the one who mathematically predicted this light behavior. There are arcs stretching across large portions of cluster images, arcs so bright they can be photographed with relatively modest telescopes. And in all these cases, when calculating how much mass would be needed to produce the observed lens and comparing it to the visible mass of the cluster or galaxy acting as lens, the result is always the same. Visible mass is insufficient. There is far more there than eyes can see. There is also weak gravitational lensing, which does not produce dramatic arcs but statistically measurable distortions in background galaxy shapes. A galaxy that would appear perfectly circular looks slightly elliptical when observed through a dark matter concentration. An elliptical galaxy appears with an axis ratio slightly different than expected. Individually, these distortions are too small to distinguish from galaxies' intrinsic shapes. But when analyzing millions of galaxies simultaneously, the signal emerges from noise and dark matter distribution across the universe can be mapped with growing precision. These maps show something fascinating about cosmic structure on large scales. Dark matter is not distributed uniformly. It clumps into filaments and nodes, a network cosmologists call the cosmic web, and the galaxies we know exist at these nodes and along these filaments like pearls on an invisible necklace. The void between filaments is almost completely devoid of matter of any kind, and the Milky Way, with its dark matter halo, sits at a node in this web, at a point where dark matter filaments meet and accumulate enough mass to contain a large galaxy and all its neighbors. The local group, the galaxy collection to which the Milky Way belongs, is dominated by 2 large members, the Milky Way and the Andromeda Galaxy. Between them lies a dark matter field connecting them, and, along with visible matter, determining both their fates. That fate, incidentally, is calculated. The 2 galaxies are approaching each other, and in about 4 billion years, according to current best estimates, they will collide. Not a collision like 2 solid objects shattering and scattering, but a gradual interpenetration of stars and gas and dark matter, a dance lasting hundreds of millions of years before resolving into a new structure, likely a much larger elliptical galaxy. But that is the future. For now, the Milky Way exists in equilibrium, a word that must be understood carefully. Equilibrium does not mean stillness. The galaxy is everything but still. Stars are born and die. Supernovae explode and launch elements into the interstellar medium. Molecular clouds collapse under their own gravity. The galactic center boils with activity of a complexity we do not yet fully grasp. And yet a pattern persists, a structure remains recognizable over time intervals exceeding any human scale of imagination. That pattern persists because the forces governing it are, for now, in balance. Hot gas pressure against gravity wanting to compress it. Stars' orbital speed against the gravitational well wanting to pull them centerward. Supernova energy against gas clouds' tendency to collapse indefinitely. And underlying all this, the dark matter halo deepening the well, retaining what would otherwise escape, ensuring the dance of stars and gas continues within a gravitational container deep enough. Equilibrium looks solid when observed from outside, when seeing only the pattern and not the tensions sustaining it. But it is dynamic in that it depends on the continuity of processes that are themselves contingent. Star formation rate is not constant. Gas fueling new stars is being consumed, and though the interstellar medium is recycled by material ejected from dead stars, that recycling is imperfect. There are losses. There is gas that heats too much and escapes the disk. There is matter falling toward the center and being swallowed by the supermassive black hole residing there. That black hole, with a mass equivalent to about 4 million solar masses, is itself one of the most dramatic manifestations of a process occurring on a galactic scale. Its catalog name is Sagittarius A, a designation mixing a constellation and technical notation, and it resides at the Milky Way's geometric center in the direction of Sagittarius when observed from Earth. Woven into its history is one of the most important facts about the galaxy, that at some point in the past it was active, consuming matter at a rate producing enormous energy jets perpendicular to the disk. The Fermi bubbles are preserved evidence of those jets. They are colossal structures of hot gas and energetic particles stretching about 25,000 light-years above and below the galactic disk, two symmetric bubbles visible not in optical light but in gamma rays and microwaves. Discovered in 2010 with the Fermi Space Telescope, they immediately became one of galactic astronomy's most intriguing phenomena. Their shape, symmetry, temperature, and composition suggest they were produced by a burst of nuclear activity millions of years ago, when the black hole consumed matter at a much higher rate than today. Today, Sagittarius A is, by astronomical standards, nearly inactive. Occasionally it consumes a gas cloud drifting too close, and in those moments emits X-ray flashes detectable by space telescopes. But the era of frenetic activity seems to have passed, at least for now. The black hole sleeps, and the Fermi bubbles are like scars of intense activity that shaped the galaxy in ways we still do not fully understand. High-velocity stars are another manifestation telling a story about forces at play inside the galaxy. There are stars moving through the galaxy at speeds so great they would escape the gravitational well if not slowed. Some were accelerated by close encounters with the central black hole, receiving a gravitational kick so intense they were flung in arbitrary directions at hundreds of kilometers per second. Others were accelerated by supernova explosions in binary systems, where one star's explosion expelled its companion with all the velocity the event released. These stars travel through the galaxy like projectiles, crossing spiral arms without belonging to any, carrying the history of their acceleration event in every kilometer of their trajectory. Some, the fastest, are called hypervelocity stars, and are already at distances placing them near the galactic halo's edges, in regions where stellar density is so low they will spend most of their future existence in near complete solitude. Traveling intergalactic space without a defined destination, there is something in these stars' existence that resonates with something any conscious being can recognize: the sensation of having been launched by a force far greater than oneself, of traveling in an unchosen direction, carrying the memory of an origin left behind and unreachable. The hypervelocity star does not know where it came from, does not know where it is going. It simply follows the trajectory physics determined in the moment of a catastrophe that was not its own toward a destiny it never chose. But most stars are not like that. Most stars, including the Sun, follow roughly circular orbits around the galactic center, with small oscillations above and below the disk plane, like buoys on a slowly breathing ocean. These oscillations are too slow to be perceived on any human timescale, but they exist and are the product of the same gravitational forces determining everything else in the galaxy: the dark matter halo, the central bulge's mass, the distribution of gas and stars in the disk. The Sun is now, in this fraction of a second as this thought forms, slightly above the galactic disk's mid-plane. In tens of millions of years it will be slightly below. With each oscillation it crosses layers of different stellar density, passes through more and less populated regions of interstellar gas, moves relative to spiral arms in ways that influence, however slightly, the cosmic ray fleets reaching the solar system and perhaps Earth's climate and geology over geological eras. The galaxy and the planet are linked by this slow dance, this oscillation of tens of millions of years that no living being perceives but that may have left marks in rock layers and the fossil record. And here, at this point where cosmic scale touches planetary and perhaps life scale, the equilibrium that seems so solid begins to reveal its more delicate texture. The galaxy is in equilibrium, but it is an equilibrium of tensions, of forces compensating each other in an arrangement that took billions of years to establish and that can, in principle, be disturbed. The Fermi bubbles show it has been disturbed before. Hypervelocity stars show nuclear events can launch objects onto completely unexpected trajectories. Andromeda's approach, invisible on any human timescale but precisely calculable, shows present equilibrium is not eternal. The dark matter halo ensures cohesion, deepens the well, retains stars, sustains the pattern. But it is not immutable in principle, even if on astronomical timescales. And the galaxy that seems so permanent when observed from a planet existing for only a few billion years, that seems so solid when contemplated on a clear southern hemisphere night, is in truth a dynamic structure sustained by a balance of forces each part maintains without consciousness and without effort, simply by being what it is, simply obeying the law governing all mass in the observable universe. It is in this balance that the galaxy exists. And it is in this balance that every star, every cloud, every dust grain, and every atom that eventually became part of something capable of contemplating all this, finds its provisional position, its place in a system too vast to be grasped at once, but that reveals itself, to those who look with enough patience, as something possessing internal coherence, a logic connecting the smallest to the immense in a web of causes and consequences, tracing back to the first instant matter and energy existed. This balance sustaining the galaxy is not, however, absolute peace. It is peace that oscillates, peace that in certain regions and under certain conditions bends to the limit before yielding, allowing forces pent up for millions of years to finally express themselves on a scale erasing any human notion of grandeur. The Milky Way is calm seen from afar, seen in its totality, seen as the gentle pattern of a slowly turning spiral. But within it, in the details composing this apparently serene structure, there are processes that can only be called violent. And this violence is not a system flaw. It is an essential part of how the system continues to exist. To understand when and how the galaxy abandons its usual behavior and enters something more intense, one must first recognize that usual behavior is already extraordinary. An interstellar gas cloud floating between spiral arms is at every moment subject to pressures balancing with a precision no engineer has ever reproduced on even an infinitely smaller scale. The gas's internal pressure caused by random atomic motion pushes outward. The gas's own gravity pulls inward. Radiation pressure from nearby stars pushes in all directions. The interstellar magnetic field offers resistance to collapse. While all these forces balance, the cloud simply exists, diffuse and cold and silent. But when that balance is disturbed, the cloud begins to remember that gravity, unlike other forces, does not exhaust itself with distance in the same way. Gravity has patience, and when the disturbance is large enough, when a sweeping pressure wave or a close pass by another cloud or a star explosion a few light years away compresses a region beyond a certain threshold, something fundamentally changes. That threshold has a name, honoring a British astronomer who described it early last century. The gene's mass and corresponding gene's length mark the point beyond which internal pressure can no longer resist gravitational pull. From that moment, collapse is inevitable. An interstellar cloud's collapse does not happen uniformly. While the central region falls inward, with growing speed, filaments form, densify, fragment. A single cloud can give rise to dozens or hundreds of simultaneous collapse regions, each generating a protostar, a nascent concentration that has not yet ignited nuclear fusion but already heats up simply by accumulating mass and compressing captured gases. These intense star-forming regions are the galaxy's most chaotically productive places. They are nurseries where outgoing light is blocked by thick dust, where internal temperatures rise far faster than in outer regions, where material jets are expelled from protostellar poles at hundreds of kilometers per second, sculpting the surrounding cloud into cavities and filaments resembling abstract sculpture more than physical process. The Orion Nebula, visible from Earth to the naked eye as a soft blur in the Hunter constellation, is one such nursery. But what the human eye sees is not the nursery itself, only the illuminated edge of a much larger, much colder cloud stretching dozens of light years. Inside that cloud, hidden by dust, stars are being born now, not on a human timescale, but now in cosmic terms in the geological present, in regions the James Webb Telescope has begun revealing with a clarity that left astronomers silent when first images arrived. Seeing a protostar wrapped in a protoplanetary gas and dust disk from which planets will eventually form is seeing the galaxy in its most intense creative mode. And where there is intense stellar creation, there is proportional destruction. The most massive stars born in these nurseries, those with dozens of times the Sun's mass, live short lives and end in ways that redefine the word dramatic. A high-mass star fuses hydrogen much faster than a common star, and when hydrogen runs out, it begins fusing helium, then carbon, oxygen, neon, magnesium, silicon in a sequence lasting progressively less time. Hydrogen fusion may last millions of years. Silicon fusion producing iron in the core lasts only days, and when iron accumulates in the core, the sequence stops. Because iron does not release energy when fused, the iron core simply grows until it reaches a limit. That limit is the Chandrasekhar limit, also named after a physicist, this time Indian, who calculated it while still young during a ship voyage from India to England. When the iron core exceeds about 1.5 solar masses in a sphere the size of a city, electron degeneracy pressure, which until then supported the core against gravitational collapse, simply becomes insufficient. In less than a second, the core collapses. Electrons are forced into protons, forming neutrons and neutrinos. The core goes from city size to a few kilometers across in a fraction of a second, and the energy released in that collapse equals everything the Sun will radiate over its entire 10 billion year existence, concentrated in less than a second. That energy exits primarily as neutrinos, particles that pass through almost everything without interaction. But in 1% of cases, neutrinos interact with the star's outer layers, still falling inward, and that 1% of astronomical energy is enough to reverse the outer layer's collapse and expel them into space in an explosion we call a supernova. A supernova can, at peak brightness, outshine its entire host galaxy for weeks. A single dying star illuminates billions of grouped stars. Seen from a safe distance, it is the most luminous event a galaxy naturally produces, and the Milky Way averages 1 to 3 supernovae per century, though most are obscured by dust and invisible from Earth. The last naked-eye supernova in the Milky Way occurred in the early 17th century, observed by Johannes Kepler, who recorded it carefully and perplexedly in an era when official doctrine still claimed heavens were immutable. Kepler's supernova in Ophiuchus was visible for over a year. Before it, the supernova we now call Cassiopeia A, observed by Tycho Brahe in 1572, caused such astonishment it helped shake the Aristotelian cosmology dominating European thought. A new star in the sky, where stars were eternal, a contradiction the universe offered humanity before it had tools to understand what it had seen. Today, tools exist. Orbiting telescopes sensitive to X-rays and gamma rays continuously monitor the sky at wavelengths Earth's atmosphere blocks. Networks of neutrino detectors, buried deep in mines or installed in Antarctic ice, wait for the signal preceding visible supernova light by hours, because neutrinos travel unimpeded while the shockwave still fights through outer layers. In February 1987, detectors at 3 different global sites recorded a neutrino burst arriving before light from supernova 1987A in the Large Magellanic Cloud. 17 neutrinos detected in 13 seconds were enough to confirm decades-old theories and inaugurate a new era in multi-messenger astronomy. What a supernova leaves behind depends on the exploding star's mass. For moderate mass stars, the collapsed core remains as a neutron star, a sphere a few kilometers across with a star's mass and an atomic nucleus's density. A teaspoon of neutron star matter would weigh over 1 billion tons on Earth. These stars rotate rapidly, in some cases hundreds of times per second, and emit radio beams from their poles like cosmic lighthouses. When those beams sweep Earth, we detect regular pulses and call them pulsars. Pulsars are clocks so precise they rival Earth's best atomic clocks, and their regularity makes them useful tools for measuring universe expansion, detecting low-frequency gravitational waves, and mapping interstellar medium structure. For even more massive stars, not even neutron degeneracy pressure can resist collapse. The core continues compressing until it forms a stellar black hole, a region where space-time curvature becomes so extreme not even light escapes. Black holes' existence was predicted mathematically before any direct observational evidence. For decades, they were theoretical objects physicists debated with enthusiasm and philosophical apprehension. The first black hole image captured in 2019 by the Event Horizon Telescope, a global collaboration of radio telescopes pole-to-pole effectively forming an Earth-sized antenna, showed the shadow of the black hole at galaxy M87's center, 55 million light-years away. And in 2022, the same collaboration published the image of the Milky Way's own central black hole, Sagittarius A. Sagittarius AE has a mass of approximately 4 million times the Sun's and is located about 26,000 light-years from the Solar System near the galaxy's geometric center. It is not, astronomically speaking, particularly active. Compared to active galactic nuclei in other galaxies, which accrete material at spectacular rates and emit relativistic energy jets visible from billions of light-years away, Sagittarius A is modest, almost discrete. Most supermassive black holes at large galaxy centers spend most of their time in relatively quiescent states, accreting material sporadically when a gas cloud or star drifts too close. But when a supermassive black hole accretes material at a high rate, what happens is one of the observable universe's most energetic phenomena. Material falling toward the black hole does not fall directly. It forms an accretion disk, a flat superheated structure spinning at near light speeds, heating through friction and compression to millions of degrees. This superheated material emits intense X-rays, and along the system's rotation axis, extremely twisted magnetic fields catalyze the expulsion of collimated material jets at relativistic speeds, jets that can stretch hundreds of thousands of light-years beyond the host galaxy, injecting energy into the intergalactic medium on a scale affecting neighboring galaxies. The Milky Way bears scars suggesting its central black hole was far more active in the past. The Fermi bubbles, discovered in 2010 by the Fermi Gamma Ray satellite, are two symmetric structures stretching about 25,000 light-years above and below the galactic plane, filled with gamma rays and high-energy particles. Their origin is still debated, but the most accepted hypothesis is they were inflated by an intense accretion event at the galaxy's center, occurring millions of years ago, when Sagittarius A devoured significant material and expelled jets that slowly carved these enormous cavities in the galactic halo. They are structures only visible with space gamma-ray detection technology, completely invisible in optical light, and with dimensions far exceeding the galactic disk's thickness. Detecting these structures changed how astronomers think about a central black hole's influence on its host galaxy's evolution. It is not just the black hole's mass that matters, nor just currently observable accretion events. Past activity history leaves physical galactic scale marks persisting for tens of millions of years and likely affected halo gas distribution, star formation rates in distant regions, and perhaps even certain galactic regions' planetary systems' ability to maintain stable conditions long enough for complex life to develop. While you rest, somewhere in the Milky Way, a gas cloud that floated in equilibrium for millions of years has just crossed the gene's threshold, and the collapse that will generate new stars has already begun, silent and irresistible. At a distance light will take millennia to cross before reaching any eye capable of witnessing. Somewhere, a massive star that fused silicon into iron for only days is in its final instance before its core collapses in less than a second, and the following shockwave grants a set of atoms forged in that interior the possibility of one day becoming part of rocks, oceans, organic molecules, thoughts. Somewhere a pulsar spins hundreds of times per second, emitting pulses with a regularity no biological process could imitate, faithful to its rhythm, even if no receiver ever detects it. These phenomena that seem isolated in their magnitudes and locations separated by ungraspable distances do not, however, happen inside independent bubbles. The supernova, exploding in one spiral arm region, scatters heavy elements that will mix with neighboring interstellar gas, enriching the chemical composition of clouds not yet collapsed, of protoplanetary disks not yet existing, of planets still billions of years from forming. The shockwave propagating from the explosion may be precisely the disturbance pushing a nearby cloud past its gene's threshold, initiating a star formation generation that would not have begun without that death. Death and birth are intertwined in a way that the separation between them, so clear on a human life scale, dissolves completely on a galactic scale, and gravitational waves detected on Earth by interferometers like LIGO and Virgo, when two black holes or two neutron stars collide somewhere in the universe, arrive at space-time perturbation smaller than a proton's diameter, but sufficient to be captured by mirrors suspended in vacuum and measured with precision unimaginable 50 years ago. Each detection is a message sent by an event occurring millions or billions of years ago, crossing the cosmos without interacting with anything, arriving at instruments built by beings existing for less than an instant in universe history who developed technology to hear space-time bend around them. The Milky Way that appears stable is not indifferent to these events. It is shaped by them continuously, and each connects to others through causal chains crossing time and space scales in a way suggesting something the word system begins to describe, but that may require a language not yet existing to be fully captured. The most dramatic phenomena are not exceptions to the galaxy. They are the galaxy in its moments of greatest expression, moments when forces always present finally reach conditions allowing full magnitude manifestation, revealing that what we called calm was merely space between storms, and that storms are not cosmos interruptions but inseparable parts of its grammar. The galaxy does not exist alone. This is perhaps modern astronomy's most quietly revolutionary understanding, accumulated over decades of patient observation. The Milky Way is a node in a network, a system within larger systems, and what happens in its depths is not independent of what happens in containing structures, in orbiting galaxies, in dark matter filaments crossing intergalactic space like nerves of an organism whose anatomy we are still learning to read. The most immediate partner in this cosmic conversation is the local group, the collection of a few dozen galaxies sharing with the Milky Way a region of space and, more than that, a destiny. The local group is not just a neighborhood. It is a gravitationally bound structure, meaning its members do not participate in the universe's general expansion the way distant galaxies do. While far galaxies continue receding due to space-time expansion, local group members are bound to each other by forces overcoming local expansion. They move, influence each other, and in some cases approach inexorably. Andromeda is the most dramatic case of this conversation. The local group's largest galaxy, it lies at a distance of approximately 2.5 million light-years and is moving toward the Milky Way at a speed of just over 110 kilometers per second. In human terms, that seems fast. In cosmic terms, it is a slow, inexorable motion already underway for billions of years. What makes this approach fascinating is not just its inevitability, but what it reveals about how systems interact long before physically touching. The two galaxies already affect each other now, in this moment, through gravity. Both their dark matter halos, vastly larger than visible star and gas disks, already overlap to some degree. Gravitational tidal streams each exerts on the other are already on subtle scales influencing peripheral gas distribution, satellite galaxy motion, perhaps even certain edge stars' trajectories in each system. Interaction does not begin at collision. It is already happening softly and distributed across distances the human mind cannot easily visualize. The most detailed model of this future merger, built with computer simulations accounting not only for star and gas gravity but also dark matter distribution in both galaxies, suggests the first close encounter will occur in about 4.5 billion years. But that first encounter will not be the end. The two galaxies' nuclei will swing apart, return, oscillate, and eventually, after perhaps another billion or 2 years, merge into a single elliptical structure some astronomers have informally called Milkomeda or Andromeda Way. The Sun will likely survive this merger. Distances between stars are so vast direct stellar collisions would be rare even in the merger's apparent chaos. But orbits would be completely reorganized, and the emerging galaxy would be unrecognizable. What this future merger tells us about the present is important. The Milky Way's apparent stability is already in part the result of past mergers. The galaxy we inhabit today has absorbed dozens, perhaps hundreds, of smaller galaxies throughout its history. The thick stellar halo surrounding the disk, full of stars in chaotic orbits, not following the main disk's organized rotation pattern, is a cemetery of assimilated galaxies. Some stellar streams, visible as faint star bands distributed around the galaxy in large arcs, are remnants of satellites progressively destroyed by the Milky Way's tidal forces before being fully incorporated. The most famous of these streams is associated with the Sagittarius dwarf galaxy, currently being absorbed. Though its original structure has been completely stretched and fragmented, its stars continue tracing a huge orbit around the galactic center, forming a faint spiral of stellar material crossing the galactic disk at least twice. The Sun may be near one of these passages, and some researchers suggest periodic perturbations in the Oort cloud, the vast comet cocoon surrounding the solar system, could be linked to these passages. If true, then events occurring on galactic scales, a satellite galaxy's destruction over billions of years, could have indirect consequences for the inner solar system, perhaps even for comet entry frequency, perhaps even for Earth mass extinction events. The causal chain connecting dwarf galaxy assimilation to a comet impact on our planet is long and uncertain, but not impossible. It is the kind of connection giving the concept of system unexpected depth. Feedback between different galaxy components operates in cycles anchored in very different timescales. In shorter cycles, developing over a few million years, we have the relationship between star formation, stellar winds, supernovae, and interstellar medium structure. A molecular cloud contracts, forms stars, massive stars, ionize surrounding gas with ultraviolet radiation, creating luminous, ionized hydrogen regions, then explode, sweeping remaining gas away and creating hot material bubbles, expanding into the interstellar medium. That expansion compresses gas in adjacent regions, can trigger new star formation rounds, and so the cycle continues, propagating across the galactic disk like waves on water. On scales of tens to hundreds of millions of years, behavior changes character. Density waves creating spiral arms have swept the galactic disk multiple times. The Sun, in its orbit around the galactic center, has completed dozens of laps and crossed spiral arms multiple times. Each arm crossing means increased gas and young star density nearby, meaning higher probability of disruptive gravitational encounters for the solar system, higher radiation density from nearby massive stars, higher probability of relatively close supernovae. Spiral arm passages are, therefore, periods of higher relative risk for planetary systems like ours, not catastrophically most times, but statistically relevant over billions of years. On billion-year scales, the larger cycle is the galaxy's own chemical evolution. Initially, gas was almost exclusively hydrogen and helium, elements produced in the Big Bang. First star generations had no rocky planets because necessary elements simply did not exist in sufficient quantity. Those first stars, supernovae, launched into space the first carbon, oxygen, silicon, iron nuclei. Each subsequent star generation was born from slightly richer gas, slightly more capable of producing complex planets, slightly more favorable to chemistry, eventually leading to what we call life. The Milky Way is richer in heavy elements today than 10 billion years ago, and that richness is not uniformly distributed. Inner regions, where star formation and death cycles were more intense throughout history, are more enriched than outer regions. The distribution of potentially habitable worlds in the galaxy is, therefore, a function not only of temperature and radiation, but also of each region's chemical history, the patient accumulation of elements over star generations. Sensitivity to initial conditions is one of the most sobering aspects emerging when trying to understand the Milky Way as a system. There is a fundamental limit to predictability, not just practical, related to instrument quality or computer capacity, but theoretical, embedded in the nature of gravitational dynamics in many body systems. The three-body problem, already known from classical mechanics, demonstrates that even three masses interacting gravitationally can exhibit chaotic behavior, where infinitesimal initial condition differences lead to radically different trajectories over time. A galaxy contains on the order of 200 to 400 billion stars. The word chaos in the technical sense acquires here an amplitude exceeding any everyday intuition. This does not mean nothing can be predicted. It means there is a predictability hierarchy. Collective large-scale behavior, general disk rotation, approximate spiral arm positions, average star formation rate, are statistical properties emerging from billions of objects' average behavior and can be modeled with relative confidence. But an individual star's fate over billions of years, its precise trajectory, close encounters it will have, comets it might eventually send toward an orbiting planetary system, all this lies beyond the predictability horizon, not because models are too weak, but because sensitivity to initial conditions irreversibly amplifies any uncertainty over time. This fundamental limitation is not science's flaw, it is, in a way, one of its most profound revelations. The universe is not a clockwork mechanism in the Enlightenment philosopher's sense, where knowing the present state would suffice to deduce the future state with arbitrary precision. The universe is a system where order and unpredictability coexist at different scales, where deterministic laws produce behaviors that, for all practical purposes, are irreducibly open. The Milky Way rigorously obeys gravity in each of its stars. And yet the collection of these rigorous obediences produces a history that could never have been completely predicted in advance, and continues to surprise observing instruments. Something contemplative emerges when taking enough distance from all these details, when letting time and space scales settle in the mind's silence. The Milky Way's beauty as a system lies not only in its grandeur, it lies in the coexistence of simple rules and unexpected results, determinism and openness, immense scales and delicate connections. A supernova exploding thousands of light years away may, through a sufficiently long event chain, contribute to an atmosphere's composition on a planet not yet existing. A galactic disk's differential rotation, an emergent property of billions of individual trajectories, produces spiral arms that in turn organize where stars are born and therefore where planets form, and therefore where conditions for complex matter organization become possible. What is comprehensible in this system is exactly what allows us to trace these connections. Gravity, thermodynamics, nuclear fusion laws are the same throughout the galaxy, and it was precisely this uniformity that made it possible for beings on an obscure planetary system at a modest spiral arm's edge to deduce the whole structure. What is surprising is that these simple laws, applied repeatedly in different contexts across unimaginable time and space scales, continue producing arrangements no model fully captured before observation. Each new telescope generation reveals details previous models did not predict, not because models were wrong, but because real system complexity permanently exceeds what any specific model can contain. Supernova shockwaves interact with magnetic fields, interacting with cosmic rays, interacting with gas influencing star formation, producing new supernovae. Black holes in satellite galaxy centers interact with dark matter halos, influencing gas distribution, determining where next star generations will be born. Residual heat from the galactic core affects cold cloud structure in peripheral regions, with a million-year delay, like an echo crossing the entire galaxy before being felt at the margins. Everything is connected by causal lines crossing space at various speeds: light speed for photons and radiation, much slower for gas pressure waves, slower still for gravitational perturbations propagating through large star populations' orbital reorganization. The galaxy's rhythm is multiple. There is the millisecond rhythm of pulsars spinning dozens of times per second, distributing energy to the interstellar medium. There is the million-year rhythm of star formation waves crossing spiral arms. There is the billion-year rhythm of chemical evolution, metal accumulation, slow cold gas depletion, and gradual star formation rate reduction across cosmic history. All these rhythms coexist, overlap, interfere with each other, and the galaxy's current state is the sum and product of all of them operating simultaneously throughout its entire history. There is an underlying order to all this, not an order readable directly on the surface, not a simple order of gears and wheels fitting with machine-like predictability, a deeper order expressing itself through complexity rather than despite it, an order manifesting in statistical regularities, in laws applying equally in every corner of observable space, in relations between quantities remaining constant while everything else varies. This order is what makes science possible, what makes it possible for patterns recognized in Earth laboratories to be valid in the galaxy's most remote regions. And there is something in this order waiting, so to speak, at the edge of what has been said so far. Not a ready answer, not an equation closing the question, but a guiding thread crossing every scale, every system, every feedback described. A principle not in any specific phenomenon's details, but seeming to cross them all, like a fundamental note persisting beneath a complex melody composed over it. Laws governing hydrogen fusion in a star's heart are the same governing the Big Bang. Gravity holding the solar system is the same organizing galaxy motion in clusters. Thermodynamics limiting lab engine efficiency also limits what stars can do with produced energy. This uniformity is not trivial. It is the most extraordinary fact of all, so every day for physics it often escapes deserved contemplation. Behind scale, complexity, supernova's fierce beauty, and spiral arms' silent delicacy. Behind feedback cycles connecting galaxy center to cold margins and billion-year past to not yet existing future, there is something unifying. Not as metaphor, not as philosophical hope, but as a fact physics continues confirming in every new domain explored. Something unchanging when scale changes. Something present at the first instant and present at the last. Something naming hastily would impoverish. This unchanging something begins revealing its nature when we stop seeking it only in objects and start seeking it in relations between them. The Milky Way is not a star collection, it is an interaction collection. And what makes these interactions possible, what regulates them, what keeps them within recognizable limits, across entire geological eras, is a feedback web operating at all scales simultaneously, some amplifying what exists, others containing what could destroy everything. Feedback is a process where something's result returns to its origin and modifies what happens next. In human daily life, this is familiar in subtle ways, like when a cold night leads someone to cover up more, and heat accumulating under blankets encourages the body to relax even more deeply, deepening sleep. Result feeds cause. In the Milky Way, this same principle operates on scales defying imagination, but obeys the same elementary logic. Consider star formation. When a cold gas cloud begins contracting under gravitational influence, it generates heat. That heat could interrupt contraction, since hot gas resists compression far more vigorously than cold gas. But if the cloud is dense and opaque enough, heat gets trapped and pressure rises until nuclear fusion begins. When fusion starts, it releases energy in all directions, heating surrounding gas, pushing it away, dispersing material that could have formed other stars. Thus, a star's birth inhibits nearby stars' birth. This is negative feedback, a control mechanism, a natural break preventing the galaxy from consuming all its gas in a single catastrophic star formation episode. But there is also the amplifying side. When massive stars die in supernovae, their shockwaves compress neighboring gas clouds, triggering new gravitational contractions. One star cluster can generate conditions for the next. One generation's death announces the next's birth. This is positive feedback, a self-amplifying process, spreading stellar activity like waves on a disturbed lake. The Milky Way does not form stars uniformly and constantly because these feedbacks create pulses. Intense activity regions followed by relative rest, cycles repeating over hundreds of millions of years. The galactic center adds another layer to this force conversation. The supermassive black hole residing there, with mass equivalent to about 4 million suns, is not a passive devourer. When material falls toward it in sufficient quantity, it heats and accelerates so much it emits energy jets at perpendicular angles to the galactic plane. These jets can ionize gas at enormous distances, interrupting star formation in entire regions. It is a governor in the mechanical sense, a device responding to excess with a counterforce restoring balance. The galaxy has memory. It records what happened before and adjusts what happens now. When the black hole rests, gas cools and falls towards it again. This feeds new activity, which again heats and disperses gas, which again stops feeding the black hole, which again rests. It is a breathing cycle pulsing, keeping the galaxy's center in creative tension, never completely quiet, never completely overflowing. And this central pulse resonates at galaxy margins with 100 million year delay. Like a bell echo taking so long to arrive, the listener forgot a bell existed. Feedback between stars and interstellar medium operates on an equally elegant scale. Stars produce stellar winds, constant charged particle flows expanding outward, heating diffuse gas between them. That heated gas resists condensation. But where gas cools enough to condense, it forms molecules. And where there are molecules, there is possibility for complex chemistry, interstellar dust, grains reflecting starlight and coloring nebulae with red and blue tones no human palate can fairly reproduce. Interstellar dust is not decorative detail, it is a functional galaxy component. Dust grains serve as surfaces where molecules form far more easily than in pure vacuum, because solid surfaces catalyze reactions that in free space would take too long to occur by chance. Thus, dust produces molecules. Molecules form more complex clouds. Complex clouds, cooled by their own infrared emissions, contract more easily. Contractions generate stars. Stars produce dust when dying. Dust facilitates molecule formation. Cycle closes and repeats. When entering the molecular level, the Milky Way reveals chemical richness that would be surprising if not so fundamental. In dense molecular clouds, where starlight does not penetrate intensely enough to break chemical bonds, astonishingly complex molecules accumulate. Not just molecular hydrogen, not just carbon monoxide, but simple organic molecules, carbon chains, alcohols, aldehydes, even prebiotic amino acids floating between stars in complete silence. The galaxy is a chemistry lab operating near absolute zero, under densities impossible to replicate in any Earth vacuum chamber, over timescales making any human experiment an insignificant fraction of its method. Carbon deserves special contemplation in this context. It is the fourth most abundant element in the universe by mass, but its importance to complex chemistry exceeds any abundance measure. Carbon's ability to form 4 simultaneous bonds with other atoms, including other carbon molecules, allows it to build chains, rings, 3-dimensional networks of a variety no other element can match. This element was forged inside intermediate mass stars through a triple fusion process uniting 3 helium nuclei into 1 carbon nucleus. It took decades to understand and, when first described mathematically, revealed something disturbing and wonderful simultaneously. It only works because carbon has a specific energy state allowing the reaction to occur. If that state were slightly different, carbon would be extremely rare in the universe, and complex chemistry as we know it simply would not exist. This is not a mystical statement, it is a physical observation. The universe has the properties it has. Carbon exists because quantum physics laws allow it to exist, and because carbon exists, and because stars synthesize and disperse it when dying, and because interstellar medium collects and redistributes and combines it with other elements into increasingly elaborate molecules, there is possibility that chemical complexity reaches a threshold beyond which it organizes into structures processing information, reacting to environment, replicating, eventually looking at the sky and asking where they came from. The Milky Way as an integrated system is an entity processing matter and energy through cycles fitting with precision seeming planned but merely resulting from invariant laws operating over sufficient time. Gas falls toward galactic plane. Plane converts part of that gas into stars. Stars process hydrogen into heavier elements. Supernovae disperse those elements back into interstellar medium. Enriched interstellar medium forms new star systems richer in heavy elements. Each star generation is chemically more sophisticated than the previous. Universe is becoming more complex over time, and galaxy is this process's engine. This gradual enrichment has a consequence worth contemplating in silence for a moment. First, stars forming right after Big Bang were composed of almost pure hydrogen and helium. There was insufficient carbon for complex chemistry, no oxygen to combine with carbon and form liquid water on any planet that might exist, no iron to build planetary cores with magnetic fields protecting surfaces from radiation. Young universe was a place of great beauty, certainly, of enormous bright stars lasting only millions of years before exploding in spectacular supernovae, but it was an unlikely place for life chemistry as we know it. That chemistry only became possible after several star generations worked silently to enrich interstellar medium with necessary elements. The Sun is at least a third-generation star. Iron in its core, carbon in organic molecules of organisms inhabiting its third planet, calcium in bones, phosphorus in DNA, oxygen in every breath, all forged in stars dying before solar system existed. All traveled through interstellar medium, compressed in molecular clouds, crossed gravitational collapse process giving birth to sun and planets, differentiated and reorganized over billions of years of geology, volcanism, impacts, ocean chemistry, eventually taking forms that breathe and think, and sometimes on clear nights look up and feel something they lack words to fully name. Emergence is the phenomenon where simple rules applied repeatedly in large numbers generate patterns no individual rule could predict or explain alone. A single water molecule has no temperature. A single gas particle has no pressure. A single star does not define a spiral arm, but billions of water molecules have temperature, billions of gas particles have pressure. Billions of stars orbiting in a gravitational field with differential rotation and density waves build spiral arms persisting for hundreds of millions of years. The Milky Way is an emergent object in its entirety. Its spiral shape was not designed, its star formation rates were not calibrated by external intelligence, its feedback cycles were not programmed. They emerged from gravity, thermodynamics, nuclear fusion, electromagnetic radiation, and time, only that. And from that set of cold impersonal laws emerged something having form, having rhythm, having history, having within it at least one planet where matter developed capacity to contemplate the whole it is part of. Synthesis offers itself now not as conclusion closing but as opening deepening. At bottom, Milky Way is simply universe learning to know itself through matter organized by time. Each star is an organization act. Each supernova is a redistribution act. Each molecular cloud is an archive of unrealized possibilities. Each planetary system is an experiment. And consciousness emerging at some point in this process is not isolated accident, but most elaborate expression known so far of a tendency seeming inscribed in physics laws themselves. Matter's tendency to organize into progressively more complex structures whenever conditions allow. Spiral arms opening at journey's start, those luminous star formation bands making galaxy recognizable from afar are organization waves. Central bulge, dense and ancient, is galaxy's deepest memory, record of first stars, first metals, first explosions scattering ingredients for everything following. Old star halo surrounding disk is time witness archive of epochs when galaxy was different and night sky preserves as ancient light. Dark matter permeating everything invisible and silent is skeleton giving galaxy shape long before stars lit it. Cold gas at outer disk edges where density drops and star formation becomes sporadic and timid is future material, not yet organized. Still awaiting right gravitational perturbation, right density wave, slow cooling, eventually initiating another star generation. At those silent edges, time operates with slowness, having no human equivalent, processes taking tens of millions of years to advance a single step. Patience inscribed in space structure, and Sun, situated about 2/3 of galactic radius from center, orbits Milky Way with periodicity of 220 to 250 million years. This period is called galactic year. Throughout Earth history, Solar System completed just over 18 to 20 of these orbits. Each time completing one, crossed different disk regions, different gas and dust densities, different cosmic radiation rates, different proximities to active star formation regions. Hypotheses suggest these variations in Sun's galactic neighborhood along its orbit may have influenced Earth climate, comet flow to inner solar system, perhaps even mass extinction rhythms. Earth is not impermeable to galaxy, it breathes with it. There is something deeply stabilizing in understanding this. Not immobility stability, not peace of what does not move, but stability of system finding its rhythm, oscillating within limits, absorbing perturbations, and returning to recognizable forms over eras. Milky Way survived collisions with satellite galaxies, absorbed star streams from smaller systems approaching too closely and undone by gravitational tide, survived supernovae shining with billions of suns' luminosity for days near neighboring star systems, and continues, deformed, enriched, slightly different each era, but recognizable, continues. You, listening now, are inside this system, not as external observer, not as someone contemplating galaxy from outside, but as expression of it. Atoms forming your body were processed by stars dying before sun existed. Consciousness with which you perceive this moment is universe turning inward with curiosity only it could generate. You are not separate from Milky Way. You are one form it took to examine itself. This is not poetic metaphor offered to comfort, it is precise description of material continuity between star and being contemplating it. Silicon in rocks of planet you inhabit was forged in stars. Iron circulating in your blood came from supernovae. Nitrogen in air entering and leaving your lungs right now was synthesized inside intermediate mass stars, cooling slowly over billions of years before dispersing it. You are made of what galaxy does. You are what galaxy made. While you rest tonight, Milky Way continues turning with calm of one having enough time for everything. Spiral arms continue weaving slow patterns. Molecular clouds at disk edges continue cooling imperceptibly toward another collapse, generating another star, perhaps with planet, perhaps with conditions for another complex story. Central black hole continues in current rest, awaiting next gas flow, waking it for millennia before sleeping again. Halo stars, ancient as galaxy, continue wide-inclined orbits, unaware of heating and cooling disk below them. You are safe. Universe producing every atom of your being has nearly 14 billion years. Practice organizing matter into persistent structures. Solar system has stability crossing geological eras. Planet sustaining you has equilibrium mechanisms operating for billions of years. You are within layers of order fitting with precision no human mind designed. Everything is in order. Galaxy does not need you awake to continue work. Stars do not wait for attention to shine. Molecular clouds do not need witnesses to slowly condense into future suns. Universe works in silence, with patience knowing no haste, with consistency knowing no fatigue. While you rest, Milky Way continues slow eternal turn. It turned when ancestors slept. It will turn when unimaginable descendants sleep in nights not yet arrived. It turned before eyes existed to see it and will continue turning after all known light dissipates in deep time cold. And in this moment, this night, this small precious instant, you are part of this turn. Your breath is part of universe rhythm. You are part of this, you always were. Let day's thoughts dissolve like mist in galactic dawn. Let mind release worries seeming urgent and that on galactic year scale are smaller than eye blink. Nothing needs solving now. Nothing needs carrying into sleep. Universe cares for you with same impartiality as every hydrogen particle in every interstellar cloud. You are completely contained within it. You cannot be outside it. There is no outside. Breathe. Galaxy breathes with you. Spiral arms extend gently in dark. Stars burn calmly. Space between them vaster than thought can hold. And in that space lies quietude unnamed in any human tongue. Quietude of what exists before disturbance. Quietude of what continues after all passes. You are safe. You always were safe in this universe, taking care over billions of years to create exact conditions for you to exist tonight. Let go. Stars continue. Galaxy continues. You rest. Universe continues silent dance and we rest in its embrace. Thank you for walking with me tonight. Sleep well.